Okay, so this is going to be the first lecture on the concept of direct sum decompositions. Direct sum decompositions. Okay, direct sum decompositions. Uh, till the previous lecture, we had essentially discussed about diagonalizable operators, right? Or to be more general in a literal sense, that we try to analyze the situation when a certain linear operator on a finite dimensional vector space attains a very simpler form. Okay, that attains a very simple form. You can think of it as a matrix or as a linear operator itself, because the matrix obviously, if diagonal, is a very simple matrix, but the linear operator on its own, if if it attains a diagonal matrix form in terms of its matrix representation, then its operator behavior is also becomes very simple, right? From this lecture onwards, our goal is slightly changed. What we want to do is that we want to decompose a certain vector space into some of invariant subspaces for a certain given linear operator T, and we want to do it in such a way that the linear operator, when restricted to each of these subspaces, then it attains a very simple form. If it does so, then it's obvious that the linear operator as a whole will also attain a very simple form. Okay, so we start with our lecture. So the first thing which we are going to study is what are direct sum decomposition. So you can think this to be of topic 1. So we start with the definition. Okay. So suppose we have some k subspaces of a vector space. So let W1, W2 till Wk be the subspaces of a vector space V. Of a vector space V, we say that W1, W2 till Wk are independent. If you have a sum of this form alpha 1, alpha 2 till alpha k equal to 0, where each alpha I is from Wi, I ranging from 1 to k, implies that each alpha i's are 0. Clear? So this is the basic definition. When you have certain k subspaces, they are said to be independent. One obvious observation from here is that if what happens if k equal to 2? So if k equal to 2, then independence typically means that their intersection is only the 0 subspace. Nothing else. Right? If you have more than 2 subspaces, then you can think of it as, suppose you have k subspaces W1, W2 till Wk, then they are independent. If some Wi intersection sum of all the other subspaces excluding I. So sum of W1 plus W2 so on till Wi minus 1 plus Wi plus 1 and till Wk, this is 0. Okay, is it clear? Got it? Okay. Now if you have k independent subspaces, let W be the sum of k independent subspaces. Okay, W1 plus W2 till you have Wk, where Wi's are independent. then what is the use of this independence? So basically what happens is that then every element of W, which can obviously be written as the sum of the elements of each alpha, each element of Wi's, it attains a unique form. That's the importance of it. Okay. So we can think of it like this, that let alpha be in W. Then alpha can be written as some alpha 1, alpha 2, and so on till alpha k. Suppose alpha can also be written as some beta 1 plus beta 2 till beta k. Okay. But that implies alpha 1 minus beta 1 plus alpha 2 minus beta 2 and so on till alpha k minus beta k becomes 0. Now obviously since alpha I and beta I both are elements from Wi, so alpha I minus beta I both are elements from Wi. One second. Yeah, okay. Yeah. So this becomes 0, right? Now since alpha I and beta I both are elements of Wi, then that implies alpha I minus beta I also belong to Wi. But then that immediately implies that alpha I minus beta I must be equal to 0 for all I. Right? And that implies alpha I must be equal to beta I. Right? Therefore, the representation is unique. Okay. Therefore, W attains a unique representation. Okay. And if it attains a unique representation, then obviously you can think of W as k tuples, elements coming from Wi's, right? That's one more trivial observation. So let us come to a lemma related to these subspaces. Okay. Let V be a finite dimensional vector space over a field F. Okay. Let W1, W2 till Wk be subspaces of V, and let V be equals to W1 plus W2 and so on plus Wk. Okay. Then the following are equivalent. So the equivalent statements are: number one, that the Wi's are independent. So W1, W2 till Wk are independent. Okay. Number two is that for all j such that j ranges from 2 to k, Wj intersection W1 and so on till Wj minus 1 is the zero subspace. And number three is that if beta I is an ordered basis of Wi, 1 less than equals to I less than equals to k, then the sequence beta given as beta 1, beta 2 and so on till beta k is an ordered basis for V. Okay. Is it clear? Okay, let us not talk about V as a whole here. Let us just consider a space W. We will talk about V as a sum of these subspaces later. Let's talk about just W. So let us give a quick proof of this. Proof. Okay. So first we prove A implies B. Okay, we prove A implies B. Or I had noted them as 1, right? 1, 2, 3. So 1 implies 2. So suppose 1 happens. Then if 1 happens, what was the first statement we had given? So they are independent, right? They are independent. So let W1, W2 till Wk be independent. We need to show that Wj intersection W1 plus W2 till Wj minus 1 is equal to 0. Okay. What we can do is we can choose an element from the intersection. Okay. Let alpha be an element from Wj intersection W1 till Wj minus 1. So alpha is an element of Wj and alpha is an element of these sums, right? So that implies there exists scalars or sorry vectors alpha 1, alpha 2 till alpha j minus 1 from W1, W2 till Wj minus 1 respectively, such that alpha in Wj can be expressed as so it can be expressed as alpha equals to alpha 1 plus alpha 2 till alpha j minus 1. But from here we can have this expression, right? So it can be written as alpha 1 plus alpha 2 till alpha j minus 1 plus minus of alpha, because alpha belongs to alpha j Wj. Now what we can do is that we can just sum over zeros, choosing 0 as elements from each of the other subspaces. So we can choose 0 from Wj plus 1, 0 from Wj plus 2 and so on till Wk. And this will obviously imply 0, right? Because this part implies 0 from here. But since they are since every W1 to Wk they are independent, therefore each of these alpha i's must be 0. That implies alpha I must be 0 for all I less than equal to j minus 1 greater than equal to 1, and alpha indeed is also 0, right? So that implies that the intersection, so that is exactly what we have in statement number 2. Is it clear? Now we need to show whether 2 implies 1 or not. So what we do is that simply we let alpha I belong to Wi for all I equal to 1 to k. Okay. Consider the equation. We consider this equation 0 is equals to alpha 1 plus alpha 2 and so on till alpha k. Okay. Now what we do is that we choose some largest integer I or rather I should say j, because we have already used the index I here. So we choose an index j which is the largest integer such that alpha j is not equal to 0. Okay. So let j be the largest integer, or I should use the term largest index, such that alpha j is non-zero. Then every element alpha j plus 1, alpha j plus 2 till alpha k are all 0 elements. So that so therefore 0 is equal to alpha 1 plus alpha 2 and so on till alpha j, alpha j, right? But from here we have this implication that alpha j can be written as minus alpha 1, should keep it in bracket, plus of minus alpha 2 and so on till plus of minus alpha j minus 1, right? Is it clear? Is it clear? Okay. So what we actually need to prove is that, so what we had to prove is that wi's are independent, right? Yeah. Okay. Now observe the following, that the right hand side, this is an element of w1 plus w2 till wj minus 1, and this is an element of wj, right? So that means every element alpha 1, alpha 2, alpha j minus 1 till alpha j, they all are elements from wj intersection w1 plus w2 till wj minus 1, right? Therefore, alpha j is equals to summation over minus alpha i's, I is equals to 1 to j minus 1. This belongs to wj intersection w1 plus till wj minus 1, right? So that typically means that alpha j is 0. But we had chosen that, we had j to be the largest index such that alpha j is not 0, right? So we got alpha j to be 0. Now the exact possibility here is that you can now choose alpha j minus 1 to be non-zero, because if alpha j is 0, then j minus 1 becomes the largest integer such that alpha j minus 1 is non-zero. But on an analogous set of steps, you will again reach that alpha j minus 1 is 0. So obviously proceeding in the following form, you will obviously get to the fact that each alpha, each vector from alpha 1 to alpha j minus 1 to alpha j indeed is also 0, right? So this is the end of the proof, right? Or you can think of it in this following way, that this immediately leads us to a contradiction, to be very precise, because observe that we have chosen that alpha j is not equal to 0, right? This was our assumption, right? But here where we reach? Here we reach is that alpha j is equal to 0. So therefore a contradiction. So that means you cannot assume that there is some largest index which is a non-zero vector, right? So therefore every vector in this expression 0 equals to alpha 1 till alpha k must all be zeros, right? Yeah, I think this is more mathematically precise, yeah, and a contradictive approach. Yeah, this is more mathematically precise, correct? So we have proved the equivalence of 1 and 2. Now observe that, so let us just prove 1 implies 3. Okay. So we let 1 to be true. So what was the first statement? Is that all the wi's are independent, right? We need to show that if I choose ordered basis from each wi, then w has an ordered basis, which is the sequence of the elements of the basis bi's, where each bi is an ordered basis of wi, right? This was the statement we had, right? What we do is that, so let bi be the ordered basis of wi for each I. I'm not mentioning the index range anymore, for each I. To show that B, which is formed as a sequence of these elements beta v1 till bk, is a basis for W. Right? This is what we actually need to show. So we have this into our consideration. What we do is that we consider a linear relation between the vectors in B and equate that to 0. Okay, so basically what we do is that we can think of it in this form, that any linear relation between the vectors in B or I should say will be of the form, beta 1 plus beta 2 and so on till beta k is equal to 0. Okay, where each beta I is certain linear combination of say ij, let's say alpha j. So j ranges from 1 to the dimension, or I should say the cardinality of each bi's. Let us not mention that in fact, but it's some linear combination of these elements alpha such that alpha j's are in basis of bi. Okay, clear? Okay. But obviously, since this is equal to 0 and each b1 is an element of the basis of wi, and each wi's are independent, so this immediately implies that beta I must be equal to 0, right? So if beta I is equals to 0, then that immediately implies that this must be equal to 0. That is, summation over aij alpha j must be equal to 0. Now alpha j's are elements from basis, so they are linearly independent. So that means the scalars must be equal to 0. So that implies that aij must be equal to 0 for all I, right? For all j, for all j, for all j. But that immediately implies the fact that, so this is the summation of bi's, right? So if you consider the summation of bi's, then that implies that you can think of it in this way. Let's go to the next page. So what does this statement basically say? So this statement basically says that if you sum over i's over the bi's, equate this to 0, then you can write this as summation over i's, summation over aij's, alpha j's, this is equal to 0. But we have found that this implies that each eij is equal to 0, and we have proved this from here itself. So that means that each of these vectors alpha j's, they form a basis element of B, right? So that implies B, which is given as B1, B2 till Bk, forms a basis of, right? Proving 3 to 1 is very simple. I am leaving this. It's obviously very simple. Okay. So let's go through a quick examples, which are some obvious examples. Example number 1. So example number 1 is that let V be a finite dimensional vector space, and let V be given as alpha 1, alpha 2 till say alpha n be an ordered basis of V. Then V is the direct sum of W1 plus W2 and so on till Wn, where each Wi is the span of the corresponding vector from the basis, that is alpha I. Okay. Okay, I have not introduced this notation yet. So V is said to be the direct sum of subspaces W1, W2 till Wk, denoted as, whereas V is given as direct sum, so it's denoted as W1 plus W2 so on till Wk, where each of these, so these subspaces are independent, where W1, W2 till Wk are independent. Clear? Got it? So that's the trivial definition of a vector space being a direct sum. So this is one important example. The next important example you can think of it. This is also you people have seen this in your plus 2 levels as well. That you can write any n cross n matrix as a sum of symmetric and skew symmetric matrices, right? Because so let A belong to the set of vector space of all matrices of dimension n cross n over the field R. Or you can just take an arbitrary field F as well. Doesn't matter. You can choose an arbitrary field F as well. Right? Then we know that we can write A as A plus A transpose by 2, or I should not abuse the notation here. We should write it as 1 by 2 times this plus 1 by 2 times A minus A transpose. And we have the fact in hand that A plus A transpose 1 by 2 times this is a symmetric matrix, and 1 by 2 times A minus A transpose is a skew symmetric matrix. Skew symmetric matrices are the ones where A transpose equals minus A, and symmetric matrices are the ones where A equals to A transpose. Okay. Now one more thing to obviously observe, that any matrix, if it is both symmetric as well as skew symmetric, then the matrix is a zero matrix, right? So if I consider a vector space of all symmetric matrices and a vector space of all skew symmetric matrices, both are subspaces of, suppose this is V, so both are subspaces of V, and their intersection is the zero subspace, right? So therefore MNF is a direct sum of the vector space of all symmetric matrices and the vector space of all skew symmetric matrices. This is one important example. One more example which I have already seen when studying diagonalizability, that is, let T be a linear operator on a finite dimensional vector space V over F. Okay. Let C1, C2 till Ck be the distinct eigenvalues of T. Okay. Let Wi be the eigenspace associated to the eigenvalue Ci. Okay. Then we recall, we can relate this to, in fact, number 1 itself. Recall, if T is diagonalizable, what happens? So if T is diagonalizable, then, so we have a basis of T, then, or we can think of it as simply we had this equivalent statement, right, that T is the, or we can just come up to this in this form, that if T is diagonalizable, then the basis elements of each Wi from I equals to 1 to K, maintaining order, serves as the basis of T. But this was the third statement in the set of equivalent statements. So that typically means that W1, W2 till Wk are independent. And since T is diagonalizable, so V can be written as W1 plus W2. And since T is diagonalizable, therefore V can be written as W1 plus W2 and so on till Wk, which necessarily implies that V is a direct sum of these subspaces. Clear? Okay. Now we introduce a very important definition, which is the concept of a projection operator. what is a projection operator? So we take a vector space V. Let V be a vector space and E be a linear operator on V. Okay. Then E is said to be a projection of V, a projection of V if E squared equals to E. Okay. So this is the definition of a projection operator. One second. Yeah. So this is the definition of a projection operator. Okay. So it's basically a linear operator which satisfies the condition that E squared equals to E. That's indeed a projection operator. So now we need to analyze a few concepts related to projection operators. Projection operator serves a lot in decomposing a certain vector space into invariant subspaces. Decomposing a vector space into invariant subspaces is the topic for our next lecture. So we need to be well prepared for that in this very lecture. Okay. So observe the following facts. Let R be the range of E and N be the null space of E. Be the null space of E. Okay. So observe the following statement that if you choose an element from R, let alpha be an element from R, then that implies that E of alpha belongs to R, right? Belongs to R, right? Right. We claim that, rather first I should write the claim and then we come up with this explanation, that a vector alpha is in the range of E if and only if E of alpha is equals to alpha. Okay. How can we prove this? So let alpha be in R, then that implies there exists some element beta in V such that the image of beta under E is equals to alpha. Right? Right? But then what can we say about E square of beta? Then E square of beta is E alpha. E square of beta is E alpha, right? We need to show that E of alpha is equals to alpha, right? Okay. So E of beta is alpha. But obviously, okay, observe the following. Yeah. So E of beta is equals to alpha. E of beta is equals to alpha. But we know that E square of alpha is alpha as well, right? E square of alpha is alpha as well. So we use that fact. So that implies what is E of alpha. So E of alpha is E square of beta, which is exactly equal to E of beta, which is equals to alpha. Right? And the other way around is obvious. Because if E of alpha is alpha, then alpha is the image of alpha under the linear operator E, and so it happens to be in the range of E. Right? Is it clear? Now, what can you say about this element? What is alpha minus E alpha? What is the image of this under E? So the image of this under E is basically E alpha minus E squared alpha. But we know E squared alpha is nothing but E alpha. So it's 0. That means elements of this form, they're in the null space of alpha. Furthermore, if you choose an element which is in intersection of the range space and the null space, let alpha be in the intersection of range space and the null space, then that means the first thing we have that E alpha is 0. But alpha belongs to R as well. So that means E of alpha must be equals to alpha. Right? We write it like this. So that means alpha can be written as E of alpha, but we have proved that E of alpha must be equal to 0. So that means alpha is equal to 0. Therefore, R and N intersects only at the 0 element. Right? So we have three statements that the range space of alpha contains only those elements whose image under the operator E is themselves. The null space contains the elements of this form, and the intersection of the range space and the null space is the 0 subspace. Now observe that any alpha, let alpha be a certain vector of V. Then we can write alpha as, then alpha can be written as alpha plus we can write this as alpha plus E of alpha plus alpha minus E of alpha. Now this is an element from the range space, this is an element from the null space. Range space and null space are independent, so that implies V is a direct sum, right? Because this readily implies that V is equals to R plus N, and R intersection N is the 0 element. So this is obvious, right? Clear? Therefore, any vector space you have, you can decompose it into the range space and the null space, provided you have a projection operator. One more thing to obviously observe from here, that the way this range space and null space is typically constructed, they are subspaces of V, right? Because E is a linear operator. So the range is a subspace of V itself. Null space is obviously a subspace of the domain space V. So observe that, or rather I should state this as a statement itself, that if R and N are subspaces of V, such that V can be written as a direct sum of them, then there exists one and only one, that is a unique projection operator E, such that the range of E is this subspace R, and the null space of E is this subspace. In this case, we say that E projects V on R along N. Okay. One more observation we can bring up from here is that, what can we say about the matrix of E? Okay. Then E is typically diagonalizable. Okay. So claim that E is diagonalizable, and that is very obvious to notice. Okay. Why? Because suppose you choose a basis for R. Let alpha 1, alpha 2 till alpha R be a basis, be an ordered basis. We should use the term an ordered basis. Be an ordered basis for R, and let alpha r plus 1, alpha r plus 2 till alpha n be an ordered basis for n. So typically alpha 1 to alpha n is an ordered basis of, that is pretty obvious to observe. Then B, which is given as alpha 1, alpha 2 till alpha n, is an ordered basis for V. Now what is the matrix of E under B? So what is the matrix of E under B? So this is observable from observing how what is the coordinate matrix of E under each of these basis elements. Okay. So what is the coordinate matrix of EI when I is less than equal to R, greater than equal to 1? So what is E of alpha I? So each alpha I are basis elements of the range space, so they obviously belong to the range space itself. So it's of the form 0 times alpha 1 plus 0 times alpha 2 and so on till 1 times alpha 1, because it's obviously equal to alpha 1, right? And so on till 0 times alpha n, right? So it admits the element 1 in the ith position and 0 in all the other positions. So typically, the coordinate matrix of E alpha I, the basis is this matrix. So it's 0, 0 and so on till 1, and then you have the rest of the elements as 0. This happens in the ith position. Here I is less than equal to R, greater than equal to 1. What happens of the other alpha i's? So what is E of alpha I when I is greater than R? So it obviously 0, right? E of alpha is 0 because they span the null space. Right? So it admits 0 in all the other places as we reach the rth position. Therefore, right, so it's obvious that the matrix of E with respect to B has this form, right? So it is of the form 1, 0, 0. So when I is equal to 1, you have 0, 1, 0, 0, and this continues till the rth position, right? Till the rth position. So suppose you have 1 here, the rth position, all the elements 0, 0, right? And all these elements are 0. So it can be typically written in the block form. So it's I, 0, 0 and 0, where dimension of I is R, right? So it is basically the R cross R identity matrix. Is it clear? Okay. Before moving on, we give a quick example of how a projection operator typically behaves. Let's go through a quick example. So find a projection operator which projects R2 onto the space spanned by the given vector 1 minus 1 along the space spanned by 1, 2. Right. So what we have here? So basically, if you relate this with the definition we used just before having this matrix example of this projection operator, then basically we have here, I'm just giving a quick form. So the range of E is the span of 1 minus 1, right? And the null space of E is the span of 1, 2. So basically we have this basis 1 minus 1 and 1, 2 of the vector space R2, right? Is it clear? So what we actually do is that we just quickly come up with this matrix form, and that is everything which we need to do, right? Or we can go step by step, which is also very obvious to observe. What we can do is that We just need to find the image of the the standard basis of R2. Okay, we can do it in this following way. So how can 1 0 be written? So suppose 1 0 is written as some C1 times 1 minus 1 plus C2 times 1 2. So from here you will get that C1 is 2 by 3, C2 is 1 by 3, 0 1, if you write it as some D1 1 minus 1 plus D2 times 1 2, then that implies you have D1 as, I guess, minus 1 upon 3 and D2 as 1 upon 3, right? Now what is E of 1 0? So E of 1 0 is 2 by 3 times E of 1 minus 1, right? But E of 1 minus 1 is minus 1. So it's E of 1 minus 1 plus 1 by 3 times E of 1 2. But E of 1 2 will be 0 because that is an element from the null space. So it is 2 by 3 times E of 1 minus 1, right? But E of 1 minus 1 is again 1 minus 1 itself because it belongs to the range of E. So it's basically 2 by 3 minus 2 by 3. Similarly, E of 0 1 will be minus 1 by 3 times 1 minus 1, which is minus 1 by 3 minus 1 by 3 and plus 1 by 3. And that's everything for you, because if you have now if you choose any element from R2, so let alpha be in R2, then alpha has a certain linear combination alpha 1 E1 plus alpha 2 E2. So that means E of alpha, this is nothing but alpha 1 times 2 by 3 minus 2 by 3 plus alpha 2 times minus 1 by 3 1 by 3. So you can frame it as 2 times alpha 1 minus alpha 2 by 3 and minus 2 alpha 1 plus alpha 2 by 3. So this is the structure of the linear operator. Clear? Okay. Okay. So let us move on. Now, suppose you have a direct sum decomposition of a certain vector space. Let V be a finite dimensional vector space and let V be the direct sum of the subspaces W1 plus W2 so on till Wk. Okay. We define an operator Ej on V such that, so how do we define this operator? So we define the operator as such that for all alpha in V, Ej of alpha is equal to alpha j. Okay. So how is this definition claiming? So let us just write one more statement before defining this linear operator. You can do it in this form. So therefore, for all vectors alpha in V, there exists alpha 1, alpha 2 till alpha k such that alpha can be written as the sum of these elements. So it's alpha 1 plus alpha 2 plus alpha k uniquely. The term uniquely is important for defining a linear operator, which we just did, to be well defined. Okay, that must be a well defined definition. So let Ej be a linear operator on V such that Ej maps alpha to its jth component. We had obviously talked about this fact that if you have a direct sum decomposition, then you can obviously think of alpha as some k tuple elements, alpha 1, alpha 2 till alpha k. So we can think of each of these alpha j's here to be components of alpha, sort of. So what does this operator does? So E of j of alpha gives us alpha j. Alpha j is an element from here. Okay, so let me just add it up. So we have some alpha j plus a of till alpha. Now what is Ej square of alpha? So ej square of alpha is ej of alpha, that is ej of alpha j. Now how can alpha j be written? Now alpha j can be written as 0 plus 0 and so on till the jth component being alpha j, then 0 and so on till 0. So the jth component of alpha j is basically alpha j itself. So that's equal to so yeah, so it's yeah, so it's alpha j, right? But alpha j is nothing but ej of alpha, right? Right. Therefore, each ej's are projection operators, right? Therefore, these ej's are projection operators. Are projection operators. Clear? Clear. What is the range of ej? Now, suppose we choose an element from Wi. Okay. We know that element is in the range of ej if and only if ej of alpha is equals to alpha. Right. So if we choose an element, um, so what is uh, e of alpha j? ej of alpha j. Okay. So what is ej of alpha j? So obviously we can bring it up from this fact, right? That ej of alpha j is nothing but alpha j. So it's equal to alpha j. That implies alpha j belongs to so it is in the range of ej. And that typically gives us that the range of ej is nothing but the subspace wj. Okay, clear? Clear? Okay. Further observe what is ei of ej. Okay. Let me think it of as in this form. That is, we claim, or we can just simply say it as an observation, that observe that what is the null space of ej. Let me just cut it out. So see, V can be written as the range space direct sum the null space. The range space is wj. So what should be the null space? Because we have V as the direct sum of w1, w2 and so on till wk. So wj can be extracted out being the range space. So what does the null space constitute of? So it constitutes of the all other subspaces, right? So it constitutes of w1 plus w2 so on till wj minus 1, direct sum wj plus 1, so on till wk. But what does this essentially say us? Therefore, for all I not equal to j, ei of ej of alpha must be equal to, so it's typically ei of alpha j, this is equal to 0, right? That is ei ej is equal to 0 for all I not equal to j. Clear? Clear? Now we had alpha as written as alpha 1 plus alpha 2 till alpha k, but each alpha, each of these components alpha 1, alpha 2 can be written as e1 of alpha plus e2 of alpha, because ei of alpha is alpha I. So e1 of alpha plus e2 of alpha and so on till ek of alpha, right? But this implies the identity operator, because I of alpha is alpha itself. So identity operator is sum of all these operators till e. Is it clear? Is it clear? So we have attained certain properties. Okay? We can summarize all of these. How? So we give this as a theorem. So if V is a direct sum of the subspaces W1, W2 till Wk, then there exists k linear operators e1, E2 till Ek on V such that number 1, that each Ei is a projection operator. Each Ei is a projection operator. Number 2, Ei Ej is equal to 0 for all I not equal to j. Number 3, the identity operator is equal to E1 plus E2 and so on till Ek. And number 4, that the range of each Ei is Wi. Right? So this is simply summarization of the observations we had just previously. Right? We are concerned about proving the converse. So conversely, if E1, E2 till Ek are k-linear operators on V which satisfy the conditions 1, 2 and 3, and if Wi is the range of Ei, then V can be written as a direct sum of these subspaces. So it can be written as W1, which is the range of E1, plus the range of E2, so on till range of E. So we are concerned about proving the converse. So proof. So okay. So how do we come up with this proof? Now, since I is equal to E1 plus E2 till Ek, therefore for all alpha in V, I alpha is equal to E1 alpha plus E2 alpha, so on till Ek alpha. But E of alpha is nothing but alpha, right? So it can be written as alpha is equals to, now since the range of, so it can be written as alpha 1 plus alpha 2 plus so on till alpha k, where each alpha I is nothing but Ei of alpha, and we have in the assumption we have that Wi is the range of Ei. So Ei of alpha must be inside Wi. So alpha I is in Wi. So this means that the vector space V is a sum of these subspaces, not yet the direct sum. Is a sum of these subspaces. W1 till Wk. Is it clear? So we are just left to show that this is indeed a direct sum, okay, or rather proving that these subspaces are independent. Okay, so we try and do this. Now we have alpha is equals to, now we have alpha is equals to alpha 1 plus alpha 2 and so on till alpha k, where each alpha I are from Wi. Okay. What is Ej of alpha? That implies what is Ej of alpha. So it's basically Ej. We can write this. We can write alpha 1 having this previous expression. So it's E1 of alpha plus Ej, E2 of alpha, and so on. We reach the jth position. So it's Ej of alpha, so on till we have so we have Ej of Ek of alpha, right? But we have that Ei Ej is equal to 0 for all I not equal to j. Therefore every element except this one vanishes, right? So this implies Ej of alpha is nothing but Ej squared of alpha, right? This we typically have in hand. But also we can think of it as, we can immediately think of it as, so Ej of alpha is denoted as alpha j, so Ej of alpha j is again alpha j, so Ej of alpha is nothing but alpha j, right? Clear? Therefore, if alpha is equals to 0, then Ej of alpha, since this is a linear operator, this must be equal to 0, which is equal to alpha j. So alpha j must be equal to 0. Since j is an arbitrary index, therefore what we can say? We can say that if this sum equals 0, therefore 0 equal to alpha 1 plus alpha 2 and so on till alpha k, where alpha I is ei of alpha, implies that each alpha minus be equal to 0 for all I. Because we can just keep on doing alpha, we can just consider E1 of 0, then we will get alpha 1 equal to 0 from here. Then we can consider E2 of 0, we will get alpha 2 is equal to 0 from here. And repeating the process, we will get alpha I to be 0 for all the i's. Right? So this implies W1, W2 till Wk are independent. So we have V as a sum of these subspaces and they are independent. So that implies V is a direct sum of these subspaces. W. That is what we require to prove. Is it clear? Okay, so let this lecture be up to this much. In the next lecture, we will be coming up with the topic of invariant direct sums. Okay, so meet you guys in the next lecture.